Welcome back to the 7th week of parameterized algorithms. This week is called Miscellaneous Techniques, and the idea is to introduce you to an assortment of different algorithmic tools, all of which are important, but they don't quite fit exactly any of the themes that we have discussed in the weeks so far. So first, I want to talk about dynamic programming. You've already seen a substantial flavor of dynamic programming in our discussions of 3D compositions and so on, but here we'll be talking about a couple of different examples which are divorced from the context of 3D compositions and just emphasize how useful and ubiquitous this is as a technique. Next, we will talk about integer linear programming as a really powerful tool to design FPT algorithms. It turns out that ILP as a problem turns out to be FPT when you parameterize it by the number of variables involved. So it's going to be a fairly general tool, and again, it may not be the best FPT algorithm that you can come up with for a given problem, but usually given the versatility of the tool, it turns out to be like a quick thing that you might want to do to even just establish that your problem is FPT to begin with. Okay, so we're going to start off with dynamic programming. We'll do a couple of examples here. So this video is split into two segments. The first one, which is going to be a relatively short discussion, is going to be about the problem of set cover, and the second one is going to be about Steiner trees. So let's get started. Okay, so in the set cover problem, the setting is the following. We are given a family of sets over a universe, so we'll typically call the family F and the universe U, and we have a budget K. And this might remind you, at least in terms of just the setting, this might remind you of hitting set. And indeed, set cover in some sense can be thought of as a dual of the hitting set problem. Yeah, so what is the goal here? It's kind of the opposite of trying to hit everything. It's a goal that involves covering everything. So what we want is a subfamily that is small in terms of the number of sets in the subfamily, and it should cover the universe. And by this I mean that if you look at all the sets in your subfamily, you want every element in the universe to appear at least once. So in other words, just to make this a little more precise, the question we are interested in is if there is a subfamily of size at most k, such that when you take the union of all the sets in the subfamily, you get U, which is your original universe. Now, there are variations off of this in the sense that you might, for example, want every element in the universe to be covered exactly once, and this variant is called exact set cover. You could also look at the maximization variant, where you have, apart from the budget, also a target, let's call the target T, and you want to see if you can cover at least T elements with a budget of at most k. This is especially relevant if the answer to your original question is no. So it's a good exercise to think about some of these variations after we discuss the algorithm for the basic version that is presented here. But before we get to the algorithm, just to make sure that we are on the same page with respect to the definition, let's just go over a quick example. So here we have a universe that consists of 6 elements, and we have a family which consists of 5 sets of size 3 each. You have a budget of 3, and I want you to take a moment here to see if you can figure out if this universe has a set cover of size 3. And in fact, given the smallness of this example, you might even want to see if you can figure out all set covers of size 3, and also answer the question of whether or not there's a smaller set cover, in particular, say with just 2 sets. Take a moment here and just see if you could figure this out. All right, so you may have noticed that any pair of sets in this family actually intersect at least one element, which means that there is no set cover with 2 sets. Let me just write that down. The reason for this is if you pick up any 2 sets, because they overlap at one element and they both have size 3, you're only going to get a total of 5 elements while your universe has 6. So that's a quick way of seeing that you cannot have a set cover with just 2 sets. But what about a budget of 3, which is our original question here? So maybe we start with the set ACE, so that covers these 3 elements. BCF additionally gets us B and F. So we just need a set that contains the element D to complete this to a set cover now. So for instance, we could pick DBF, and that would be it. That would be a set cover of size 3. So you could think of this as a yes instance. Okay, so now that we've worked through this example, let's try and come up with an algorithm for the problem. So remember, we're using dynamic programming for this discussion here, and one hint is already in the name that you see here. So we think of this as dynamic programming over subsets, and let me also make the goal explicit in terms of the running time. So the goal is to come up with an algorithm that runs in time 2 to the n, with some polynomial overhead in n and m. So just to be clear, n is the size of the universe and m is the size of the family. So given this format, maybe you want to take a moment here to think about what could the DP table be, and then we could get to trying to figure out how do we want to populate it. All right, so hopefully you had a moment to reflect on this. Let's try and see what would a reasonably natural approach be. So let's recall what our ultimate target is. We want to cover the universe U using a minimum number of sets from the given family F, which is some collection of M sets. Okay. So at this point, there could be multiple approaches to trying to set up a DP table here. So I will describe one of them that I think is quite natural. So in the spirit of looking for an intermediate subproblem, instead of trying to cover the whole set, we'll just try to cover a subset. That's a smaller goal to work with, and these smaller goals will eventually build up to helping us figure out the solution for the whole problem. So we want to cover some subset, and we want to just focus on whether some subset can be covered using some partial part of the family that we have been exposed to so far. So here is a natural intermediate goal, or if you like, you could think of this as a subproblem. You want to cover only some subset of the universe using a truncated portion of the original family, which we are calling Fj. So this consists of the first j sets in the family F. You could order the family in any way you like so that this notion of the first j sets makes sense. So a quick question for you here: how many subproblems have we generated with this definition? Well, we have a choice for every subset of the universe. So if our universe has n elements, we already have 2 to the n choices for x. And we also have a choice of how much of the original family we are allowed to use up. So we have m options for the index j here. So 2 to the n times m is simply the number of subproblems that we are working with. And if you think about whether these subproblems are worth solving, well, we want to note that the final answer will lie in the subproblem corresponding to x being equal to the universe and j being equal to m. So this means that this intermediate goal actually manifests as our ultimate target, which is to cover all of U using a smallest number of sets from all of F, right? So if we are able to compute the answers to these intermediate subproblems, then we would in fact be done, because by the time we get to the end of it, we have solved the whole problem. So just to recall how this is going to work, given that we have a DP-based setup, the idea is that when we are trying to solve the intermediate goal with respect to x and j, we are going to assume that we already have access to the answers for the intermediate problems corresponding to x prime and L for all choices of x prime that are subsets of x, and for all choices of L that are strictly smaller than j. So we assume that we have these answers at hand and they can be looked up in constant time, and given that, we want to figure out what's the answer for the subproblem corresponding to the pair x and j. So that's essentially the task of coming up with the DP recurrence. And to make the description of the program complete, of course, we want to work out the base case, and we know that at the very end, the answer that we report is simply the answer to the goal corresponding to x equals u and j equals m, like we just discussed. So if these intermediate goals can be computed either in constant time or let's say even some polynomial time, then the overall running time is going to be the amount of time that you need to solve each of these intermediate goals with an overhead of 2 to the n times m, because that's the number of subproblems that we have. So hopefully this overall outline makes sense, and if it does, I would encourage you to really take a pause here and try to figure out what the recurrence should be, and then we can exchange notes when you're ready to come back. All right, hopefully you've had a chance to think through the DP recurrence a little bit. Let me begin by rephrasing this business of intermediate goals in the more standard language of DP tables. So let's say that we have a table entry corresponding to a pair x comma j, and what we want this table entry to record is the minimum number of sets from f sub j, which, if you recall, was the first j sets required to cover all of x. And let me just remind ourselves that x is a subset of the universe and j is some number that ranges from 0 to m. So m again is the size of the family that you're working with. Alright, so of course it's possible that there is no such collection of sets, so it doesn't make sense to talk about the minimum number. It's possible that this is somewhat ill-defined. So we're going to notationally use plus infinity to record the fact that it's impossible to cover x using sets from S1 through Sj. All right. So with all that said, we can get started with the base cases. So the smallest value that j can take on is 0. So let's try to figure out what t of s comma 0 will be for any subset s. Now clearly, if s is non-empty, then we cannot possibly hope to cover it if we are not really given anything to work with. So f sub 0 is the empty family. So if s is non-empty, then the answer here should be plus infinity. If s is not the empty set, and of course the empty set is a legitimate subset of the universe. So if you're working with the empty set, then 0 is okay because you have no work to do and nothing to be done. So in this case, the answer is simply 0. So that's the base case. Now let's think about the recurrence. Now to figure out what the recurrence should be, let's take a moment to imagine what our solution looks like. There are two possible scenarios that we could encounter, especially relative to what's going on with this set Sj. It's possible that your solution does not use the set Sj. In this case, it's actually a way of covering x using only the sets from 1 through j minus 1, and in fact it must be the best possible way to do this, because if there was an even better way of doing it, then that would have been what would have witnessed your solution as well. So in case your solution does not pick the set Sj, if the best way to cover X using sets from S1 through Sj in fact is only using sets from S1 through Sj minus 1, then you can actually look this up in something that you have computed already. So you could just try to cover X using just the first j minus 1 sets. So that's one possible situation that you could be in. If you are in this situation, then the answer is what is there in the table entry corresponding to the pair x, j minus 1. On the other hand, the other situation you could be in is that you do use Sj in your solution. So there's an optimal solution which involves the set Sj. Then you could think of this solution as being broken up into two parts. So you have the set Sj here, and you have the rest of the set X being covered by elements by sets from S1 through Sj minus 1. So this rest of X is really just X minus Sj, and we already again know what is the best way of covering X minus Sj using sets from S1 through Sj minus 1. So that's going to be this table entry corresponding to the pair X minus Sj, j minus 1, and our solution is going to be basically a combination of this solution along with the set Sj. So it's going to be whatever number you get from this table entry plus 1 to account for the fact that you have added the set Sj. So now you have these two possible scenarios. You of course don't know which one corresponds to the truth, but what you can do is certainly compute these two values, and then you know that the truth must correspond to the better of the two values, because you know that you're looking for the best possible way to cover X using sets from S1 through Sj. So the final answer that you report is simply going to be the minimum of these two numbers that you compute here. And with that, I think we now have a full specification of the algorithm. Now that we have completed the recurrence, this really is it. And you also know that the running time of this algorithm is going to be the number of table entries, which is 2 to the n times m, multiplied by the amount of time that you need to compute each table entry. Now, the computation of each table entry can be derived by just staring at this recurrence for a bit. So essentially, you have a couple of table lookups, and then you have a couple of operations here. And you also would need some time to compute X minus Sj. So it's a simple table lookup, but you do need to go through X and erase all the elements that belong to Sj. So that's going to be some work. But all of that is really just a polynomial overhead, so I'm going to leave it at that. Now finally, notice that the correctness of this algorithm really hinges on the accuracy of the recurrence that we established here, and hopefully the correctness of this recurrence was reasonably clear, at least intuitively, based on the discussion that we had when we came up with it. But nonetheless, just to keep this a self-contained argument, let's go ahead and actually prove this a little more explicitly. So here we have the recurrence that we used in the algorithm, and the formal framework that we want to use to establish the correctness of the recurrence is going to be induction, and in particular we want to perform induction on J. So as always with induction, you want to start off with the base case. So the base case in this algorithm was really quite straightforward. We said that x, 0 basically evaluates to impossible if x is non-empty, and 0 if x is an empty set, and there's practically nothing to prove here, so this is fine. Now, to be able to actually prove the main claim, we need some sort of a meaningful induction hypothesis. So what we are going to say is that the claim is true, meaning that T of xj basically does carry the value claimed by its semantics for all j that are smaller than the current value of j. So in particular, t of x prime comma L is indeed the best possible way of covering x prime using the first L sets for all x prime subset of x and for all L strictly smaller than j. So that's the induction hypothesis, which again is natural given that we are doing induction on j. Now, to prove the equality, we are basically going to break this up into two inequalities. The first one is that the left-hand side is less than or equal to the right-hand side, which is to say that the right-hand side is a good upper bound for the left-hand side. So I'm going to keep calling the right-hand side our estimate for t of xj, and this inequality is basically saying that this is a realistic estimate. You can actually come up with a set cover that has the value whose size is the value given by our estimate. On the other hand, the other inequality is some sort of a lower bound saying that this estimate is actually tight. You cannot do any better than what has been claimed here. So these two inequalities combined will finally give you what you want. Now, first let's show the upper bound. So let's just give these values some names. So let's say t of x j minus 1 is a and t of x minus s j minus 1 is b. So based on the induction hypothesis, what we know is that there is a collection of A sets from x1 to, sorry, this should have been, I think, S1. So S1 to Sj minus 1 that cover x. And similarly, also by the induction hypothesis, we know that there is a collection of B sets from S1 to Sj minus 1 that covers not x, but at least it covers x minus Sj. And the second statement implies that there is a collection of B plus 1 sets from, again, S1 through Sj that covers x, because we could simply take this collection of B sets here and append the set Sj to it to get a cover for all of x. So that's what we have from the induction hypothesis. So we work with, we have solutions at our disposal that have sizes a and b plus 1. So in particular, we do have a solution whose size is the smaller of the two because we have both of them. So clearly, this is an achievable estimate for sure. Now, the next thing we want to say is that this estimate is tight, in that in particular, we cannot do better than what we have on the right-hand side. To establish this side of the inequality, let's begin by talking about what's on the left-hand side. So let's call this number c, txj. So just by definition or semantics, what this means is that there is a collection of some C sets from among S1 through Sj that covers all of x. Now let's call this collection of C sets H. And let's ask ourselves, like we did when we were coming up with the recurrence, whether Sj belongs to H or not. Now, if Sj does belong to H, then what that implies is that there is a collection of C minus 1 sets from S1 through Sj minus 1 that covers x minus Sj. And this is simply witnessed by H minus Sj. So H was a collection of C sets, and we knock out 1 from it, and we are left with C minus 1. And those C minus 1 sets, of course, come from S1 to Sj minus 1, and they cover x minus Sj. So this implies that in this case, at least, what we know is that t of x minus Sj j minus 1 is going to be at most C minus 1, because you can definitely do this with C minus 1 may be better, but certainly C minus 1 is a valid upper bound. So in this case, this quantity here is going to amount to C. On the other hand, it's possible that Si does not belong to H, but this is even more direct because this implies that there is some collection of C sets from S1 through Sj minus 1 that in fact covers all of X. And in this case, we know that this quantity is going to be at most C. So with this, what we have is that no matter what the scenario is, the expression on the right-hand side is going to be at most C. Could be something that's even better if the quantity that is not under consideration actually overrides the value that is under consideration, since we're taking the minimum of both the values involved. But hopefully you can see that no matter what happens, the expression on the right-hand side evaluates to being at most C. So in particular, we could say that our estimate is going to be at most C, but that's exactly what we wanted to show. So that completes this direction of the inequality, and in fact with that we actually complete the entire argument. So this wraps up our discussion on set cover, and we are going to look at dynamic programming in action in the context of another problem called Steiner tree. So that's coming up in the next segment of this video, so I'll see you there.